reflection and transmission. We're going to talk first about reflection at a boundary. This is where a wave hits and comes back. That initial pulse is called the incident pulse. The energy that comes back is the reflected pulse. Some energy is transmitted to the pole in real life, if this is, for example, a pole, like a picture like this. Okay, and in that case, the pulse is going to be a smaller amplitude because the amplitude is related to the energy. But we aren't always going to talk about that. We might call these ideal collisions where you've conserved energy as well. All right, so here's a picture. If you have a fixed end and a rope attached to it, you can study the behavior of what happens at that reflection point. All right, if that end is fixed to the pole, the reflected pulse is inverted. That means it's upside down from what it was. The wave speed and the wavelength do not change because the wave speed is a property of the medium, and the frequency of the wave has not changed, therefore the wavelength has not either. Like I said before, in real life strings, the energy eventually dissipates. In physics, we may simplify it to the fact where there is no friction in the system or the string does not dissipate that energy. Okay, so here's the picture of an incident pulse and the inverted reflected pulse at a fixed end. All right, reflection with a free end. This is where the other end is free to move up and down the pole. In that case, the reflected pulse is not inverted. Okay, so here's what that looks like, the incident pulse, but then it comes back, and because that ring on the pole is free to move up and down, it actually sends the pulse back in the same shape it was coming in. Transmission. So the energy that was transferred to the pole is called transmission. If I connected two slinkies of different densities, there would be a combination of reflection and transmission. So if we went from a less to more dense setup, right, that boundary there in the middle is noted. The reflected pulse, some of the energy that comes back, it's inverted. And the transmitted pulse, because it's a more dense medium, the wave speed becomes slower, and because the frequency didn't change, the wavelength is also smaller. The reflected pulse has the same speed and wavelength as the incident pulse because the speed is a property of that medium and the frequency hasn't changed, so the wavelength stays the same. So here's this in a picture of what it looks like, the incident pulse coming in, and then after the interaction at the boundary, some reflection. You'll notice it has less amplitude than the incident pulse. The rest of that energy was transmitted into the more dense string. So now let's look if we go from more to less dense. The transmitted pulse travels faster with a larger wavelength because now the less dense medium has a larger wave speed, and so the wavelength goes farther. The reflected pulse has the same speed and wavelength as the incident pulse because it hasn't changed mediums. So here's this scenario, all right, in a picture. You'll notice here that the more dense one has lost some energy, and if you look carefully, the less dense string it's a lower amplitude than the original pulse, all right, but it will take a larger proportion of the energy because it's easier for the wave to move through it. Here are some rules of thumb, and this functions as your summary slide. The same medium equals the same wave speed, all right, that's a property of the medium, not a property of the wave itself. The frequency of the wave then will determine the wavelength in that medium. The same wave is always going to be the same frequency because it is a property of the wave. That means that the medium will determine the wave speed and therefore the wavelength for that particular wave in that medium.